Alright, welcome back. Today we'll cover a new topic on AI, on how a physical sensor to assess the position of an electric motor can be replaced by a virtual sensor. So just think for a second about the electric motors and everything from your EV to a high-end drone. They spin with this just insane precision. So you gotta ask, right? How in the world do they pull that off? How does the motor's brain know the exact position of its spinning part down to the microsecond? Well, the secret lies in a really sophisticated control algorithm. You can think of it as an unseen conductor just orchestrating the whole complex performance. That system is called field-oriented control, or FOC for short. And it's basically the motor's central nervous system. It is constantly making this tiny little adjustment to the power it's sending to the motor. But to do its job, it has one thing it absolutely has to have with no exception. It needs to know the rotor's exact position in real time all the time. So how have we always done this? You know, the old school way. Well, pretty simply, you give the system a physical eye to actually watch the rotor. Okay, so if you look at this diagram, you can see the traditional solution right here, highlighted in green. It's the physical position sensor, a piece of hardware that's literally bolted onto the motor. Its whole purpose in life is just to watch that rotor spin and feed that position data back into the control system. Sounds simple enough, right? But yeah, it comes with a whole bunch of problems. For starters, that physical sensor, it costs money. It adds to the price tag of the final product, and it takes up space, which is a huge deal in something very tiny like a drone. Plus, it's another physical part, right? Another thing that can wear out or break, which hurts reliability. It just makes the whole design and manufacturing process that much more complicated. So you just know that there has to be a better way. And of course there is. The better way is to, well, just get rid of the physical part altogether and replace it with something virtual, something purely made of code. So this brings us to the star of the show, the virtual sensor. What is it? Well, instead of physically measuring the rotor's position, it's a super smart AI algorithm that estimates it. It acts like a detective looking at clues the system already has, like the voltage and the current flowing through the motor. And from those clues, it predicts the position. Okay, let's go back to our control diagram. Remember that physical sensor we pointed out before? It's gone. And in its place, you see the orange block? That's a neural network. This little bit of AI takes in the electric signal, the stuff we're already measuring, and it spits out a highly accurate prediction of the rotor's position. It does the exact same job as the piece of hardware it just replaced. Okay, that sounds amazing, but how do you actually create an AI that can pull this off? You have to teach it. So let's walk you through how it's done. It really breaks down into a pretty straightforward 3-step process. First, you have to generate the data. Think of it as writing the ultimate textbook for the AI to study. Second, you train the AI. That's the study session. And finally, you test it. You give it a final exam to see if it actually learned anything before you let it out into the wild. Alright, so step 1, creating that textbook. This is maybe the most important part of the whole process. Engineers don't even use a real motor at first. They use a simulation, a perfect digital twin of the real thing. They run this virtual motor through literally every scenario you can imagine, what's called a sweep operation. They crank the speed from 0 all the way to 100% under all sorts of different loads. And the whole time they're recording everything, the voltages, the currents, and here is the key, the true rotor position. Okay, the textbook is written. Now it's time for your AI to eat the book. So the specific kind of AI we will use here is called an autoregressive neural network. Now, all you really need to know is that it's just really good at finding patterns and data that changes over time, which you know is perfect for a spinning motor. You feed it that giant dataset you made, and it's just to figure out the super complex, almost magical relationship between the electricity going in and the rotor position coming out. Now, this is pretty standard practice in the AI world, but you don't use all of your data for the study session. You split it up. About 70% is for the main training, another 15% is used to make sure that it's on the right track, and the last 15% that's kept under luck, it's for the final exam. And that brings us to the big finale, the final exam. After all this data crunching and training, it's time to see if our virtual sensor can actually perform in a realistic test. So it's the million-dollar question, right? After all that work, does it actually work? Can a chunk of code really truly replace a physical piece of hardware and be just as good or maybe even better? And here are the results. This graph is the proof. The green line, that's the real actual position from the physical sensor. The ground truth, the red line, that's our prediction. It means, just look at that. They are basically right on top of each other. It's a perfect match. It actually worked. So what does this mean in the real world? Well, the payoff is huge right off the bat. It's cheaper, you don't have to buy a physical sensor. Believe it or not, the AI can actually do much more precise than some hardware. Your reliability goes way up because it's one less physical part that can break, and you free up all this valuable space, which is a total game changer for compact designs. These AI-driven sensorless solutions, they are not just an alternative, they can actually be a better alternative to physical hardware. And that's a huge deal. It's a fundamental shift in how we think about building smart machines. And that really leaves us with one last question to chew on. If intelligent software can replace a critical sensor in a high-performance motor, what's next? What other physical hardware in our lives, in our cars, in our phones, our home, is about to be replaced by just a clever piece of software? Something to think about. All right, thanks for tuning in. And if you liked this video, please hit subscribe and share it with others. Bye-bye.